This content is for educational and informational purposes only. It is not professional advice, medical, legal, or technical. Viewers should do their own research before trying anything mentioned. Results may vary depending on conditions. The content is based on historical, scientific, or publicly available information. A $1 object. Something you've probably seen in your kitchen, a corner store, or even thrown away without thinking twice. But what if I told you that this simple, almost worthless looking material is part of a concept that could quietly reshape how we think about energy storage, and even challenge the direction big companies like Tesla are heading? No tools needed, no professional required. Just a simple idea anyone can understand. And the strange part is, it's been sitting in plain sight for decades. Most people don't notice it, because it doesn't look like innovation. It looks too ordinary to matter. But that's exactly where this story begins. Right now, advanced battery systems can cost hundreds or even thousands of dollars per unit, depending on scale. Electric vehicles rely on complex lithium-based systems that require expensive mining, refinement, precision engineering, and controlled environments. A full EV battery pack replacement can reach thousands of dollars. Even small-scale energy storage systems for homes can cost more than a used car in some cases. Now contrast that with something worth around $1 in bulk form. Salt, carbon-based material like graphite, basic metals like copper or aluminum foil. Materials so common that industries treat them as background components, not headline innovations. Individually, they look insignificant, but together they unlock a very old idea that scientists have explored for over a century: simple electrochemical energy generation using abundant materials. And that's where things start to get interesting, because before modern lithium batteries existed, early energy storage experiments were already happening using basic chemical reactions between metals and electrolytes. These were not powerful enough for modern electronics, but they proved something important. Energy storage doesn't always require rare or expensive materials. It only requires the right interaction. Now here's where history quietly steps in. In the early development of electrical science, researchers explored simple wet cells and primitive batteries using salt solutions and metal plates. These early experiments were foundational in understanding how ions move and how chemical reactions can produce electricity. Over time, technology evolved. Industries shifted toward higher density energy systems. Lithium-ion became dominant because it offered better performance, stability, and scalability. But the trade-off was cost and complexity. And that's where the forgotten method idea comes in. Not that modern batteries are wrong, but that simpler approaches were never fully erased. They were just overshadowed by performance-driven innovation. And in recent years, researchers, hobbyists, and even industrial designers have revisited these simple material combinations, not as replacements, but as alternative concepts for low-cost energy storage in specific use cases. Some describe it as good enough energy, rather than maximum performance energy. Now let's break down the simple science behind why this matters. At its core, a battery is just a controlled chemical reaction. Two different materials interact through an electrolyte, creating a flow of electrons. That flow becomes electricity. Nothing magical, just physics and chemistry working together. When you use common materials like saltwater solutions and basic metals, the reaction is weaker compared to advanced lithium systems. But it still works. And more importantly, it uses extremely low-cost inputs. That's the key idea. The problem most people face is assuming energy technology must always be expensive or highly engineered. But nature doesn't care about price tags. Reactions either happen or they don't. Now let's talk about why the problem exists in the first place. Modern energy systems aren't expensive just because of materials. They're expensive because of optimization. Industries spend billions improving efficiency, durability, and safety. That means purification processes, rare material extraction, strict quality control, and massive supply chains. You're not just paying for the material. You're paying for performance, safety, and consistency. So when people see a $1 concept, they often misunderstand it. It's not competing with high-performance systems directly. It's competing in a different category, accessibility and simplicity, and that distinction is important. Because in technology, there are always two paths. One path pushes maximum performance, the other pushes maximum availability. Now let's go deeper into a soft historical angle that many people overlook. During multiple periods of scientific development, simple battery concepts were used in educational settings and early industrial experiments. They were never meant to power entire cities or electric vehicles, but they were crucial in demonstrating how electricity could be generated from basic materials. Over time, as industries scaled up, these simple systems were gradually replaced in commercial use. Not because they stopped working, but because better performing alternatives became available. That's how progress usually happens. Old methods don't disappear, they just become less visible. Now imagine a modern version of that same principle, not a replacement for advanced EV batteries, but a supplemental concept. something that could be used for low power storage, emergency systems, educational tools, or experimental energy models. That's where interest in low-cost material energy systems continues to appear in research discussions and maker communities. So how does it actually work in simple terms? When two different conductive materials are placed in an electrolyte environment, ions begin to move between them. One material tends to lose electrons while the other gains them. This imbalance creates electrical potential. That potential can be captured as usable energy. Again, nothing exotic, just controlled imbalance. Now, why does this matter in everyday life? Because many energy problems are not about maximum power. They are about accessibility. Think about remote areas, emergency backup systems, educational demonstrations, off-grid experiments, low-cost prototypes. In those situations, expensive systems are not always practical. This is where simple material-based concepts become interesting again. But there's also an economic layer to this story. Large industries don't just build technology, they build ecosystems. Manufacturing, maintenance, warranties, replacements, and upgrades all form part of the business model. So while advanced systems offer incredible performance, they also come with long-term service structures. Meanwhile, simple systems rely on widely available materials, but lack the refinement and durability required for demanding applications. It's not about one replacing the other, it's about different needs. Now let's walk through a very simplified conceptual guide so you understand how this idea is explored in basic science environments. First, identify two different conductive materials that behave differently in a chemical environment. Second, introduce a liquid medium that allows ion movement. Third, allow a controlled reaction between the materials through that medium. Fourth, observe the small electrical output created by the chemical imbalance. Fifth, understand how multiple small cells can be combined in theory to increase output. This is not a consumer-ready energy solution. It is a conceptual demonstration of how energy can be generated from basic interactions. And that's where most people are surprised, because the principle itself is ancient, but still relevant. Now let's talk about what people commonly observe when experimenting with these ideas in controlled environments. They often report low but measurable electrical output. They also notice that performance varies significantly depending on material quality, surface area, and environmental conditions. Humidity, temperature, and material purity can all affect results. That inconsistency is one reason why industrial systems move toward more stable chemistries. But the underlying concept remains valid. And this is where the bigger insight appears. In almost every major industry, there is a pattern. Highly advanced solutions evolve from very simple foundations. And sometimes those simple foundations still hold value in specific contexts, not as replacements, but as alternatives for accessibility, learning, and experimentation. We see this in computing, where basic microcontrollers are used alongside supercomputers. We see it in transportation, where bicycles still exist alongside electric vehicles. And we see it in energy, where simple chemical cells still exist alongside advanced battery packs. Different tools, different purposes, and sometimes the simplest ones survive longer than expected. Now, before we continue, here's an important second disclaimer. This content is for educational and informational purposes only. There is no guarantee of results from any concept mentioned. Any exploration of energy-related ideas should be done carefully, responsibly, and in safe, controlled environments where applicable. Viewers are fully responsible for how they interpret or use this information. Always research and understand safety considerations before attempting or applying any method. Now stepping back into the bigger picture. When people hear about cheap energy ideas, it's easy for imagination to run wild. But real innovation is usually more gradual than dramatic. Tesla and other major companies are not competing with $1 materials. They are building systems designed for performance, safety, scale, and long-term reliability. At the same time, simple material-based energy concepts continue to inspire education, experimentation, and niche applications. Both worlds coexist. One pushes the future forward at scale. The other keeps the foundation accessible and understandable. And that balance is often overlooked, because sometimes the most powerful ideas are not the ones that replace everything else, but the ones that help us understand the basics more clearly. So when you hear about a $1 material connected to energy concepts that sound surprisingly powerful, the real takeaway isn't that it will disrupt entire industries overnight. The real takeaway is simpler. Innovation doesn't always start with expensive technology. Sometimes it starts with something ordinary that most people ignore. And if this helped you understand something new, share it with others who might find it interesting. Subscribe for more educational content like this. And always stay curious, but careful with what you explore.